Hello everyone, today we're going to be working on problem 4.154 and this problem is asking us to replace the loading by an equivalent resultant force and to specify the location of the force on the beam measured from A. So as you guys could see here, we have a shape that to determine that resultant force, we would basically be using the equation of finding the area of this shape. But since we don't really have an equation to determine the area of this shape that's given to us, we do know how to find the area of a rectangle and a right triangle because as you guys could see, we could simply cut this right here at the 3 kilonewton over meter height and then just cut it straight across, giving us a rectangle, and then from there giving us that right triangle. So that's what we're going to do. And then from there, we're going to be finding that concentrated force of those two shapes. And then from there, finding our resultant force or our equivalent resultant force. So now that we have this rectangle that we know that will have a constant loading of 3 kilonewtons per meter. Now for our right triangle, we knew that at the beginning, this was the max weight of the loading, and all of this was 5 kilonewtons over meters. But now since we cut that, we took some of that away. Now, what we're going to do to determine now the new max weight of that right triangle, we're simply just going to be subtracting from that 5 kilonewtons over meters, the 3 kilonewtons over meters, giving us that this has now a max weight of 2 kilonewtons per meter. So now we're going to be determining those two concentrated forces. We know that for a triangle or for a right triangle, better said, we know that either from the tallest side of the triangle, it's at the location is going to be 1/3 in, or from the smallest height of the triangle, we know that it's going to be 2/3 in. And since this problem is asking us to find the location of that resultant force from point A, we're going to be determining the location of all the forces based on point A. So that means it's going to be 2/3 in. So 2/3 of 6 meters is 4 meters. So it's going to be right here. That's our location of R1. And for our concentrated force of our rectangle, since it's a rectangle, we know that since it has that constant unit loading, we know that that's going to be found exactly mid-span of our beam. So half of 6 meters is 3 meters, so we know that it's going to be somewhere around here for our concentrated loading of our rectangle. So now we're going to determine the magnitude of those concentrated forces. So we know that R1 is equal to half of, we know that the right triangle has a length or a span of 6 meters. So 6 meters times, once again, we said that the highest point of our triangle is 2 kilonewtons over meters. So times 2 kilonewtons per meter. So that should give us that our concentrated force for our right triangle is equal to 6 kilonewtons. Then from there, for our rectangle, it's just the length times the height, the same as finding the area of that rectangle. So that means that we would be multiplying 6 meters by 3 kilonewtons per meter, giving us that concentrated force of our rectangle is equal to 18 kilonewtons. So from there, we would have to determine the location of each of these ones. Once again, if you guys remember what I mentioned earlier, that for a right triangle, since we're basing the locations from point A, the location from R of 1 is going to be exactly 2/3 in. So we said that 2/3 of this 6 meters is 4 meters. So our location is 4 meters from point A. And for our concentrated force, our second force, We know that's mid-span of the beam, so that's 3 meters. Started location for our second force, 3 meters. Now that we know all of that, what we're going to do to find our resultant force, it's basically just adding all of our forces. So our resultant force is equal to R1 plus R2, meaning that our resultant force is equal to 24 kilonewtons, obviously acting downwards on that beam. So from there, the only thing that's missing is since we already found that equivalent resultant force, the magnitude of that equivalent resultant force, now we just have to specify the location of the force. And to do that, what we're going to be doing is we're going to be writing this equation that's going to help us determine that location. So we're going to be writing out the equation of finding the moments or the sum of the moments about point A. So our sign convention counterclockwise is positive, and that our sum of our moments about point A is equal to the force times the distance. Here our force is going to be our resultant force, and our distance is going to be that location where our resultant force is located. We don't know exactly where that resultant force is, but we do know that it's obviously going to be on the right side of our point A. So any force that's on the right side of point A, we know that that's going to be creating a clockwise moment, meaning it's going to be a negative moment. So we know that's going to be equal to a negative. Remember, we said our moment is equal to the force times the distance. So our force is our resultant force times our distance, and our distance is that location that we're trying to determine. Now from here, what I'm going to do is I'm going to be taking this part of our equation and I'm going to be rewriting it. So we know that moment is equal to force times distance. Our force here is our resultant force, but remember, we said that our resultant force is equal to the summation of all our forces. So that means that we could rewrite this part of our equation. It's also equal to negative R1 times X1 minus R2 times X2. That would be giving you the same exact answer for the summation of the moments about point A. Once again, these are negative moments because they are also both on the right side of that point A, so it would also be giving you that negative moment, and well, it's equal to our resultant force times the location of our resultant force. So now that we know that these two equations are equal to each other, we're going to be taking this and rewriting it in just in terms of helping us find that location of our resultant force. So if we were to rewrite this for in terms of that location, it should end up giving us that the location of our resultant force is equal to R1 times X1 plus R2 times X2 all over our resultant force. So now that we have the equation that we're going to be using to determine the location of our resultant force, we're simply just going to plug in our information. So we said that R1 is equal to 6 kilonewtons per meters times we said that the location was 4 meters. From there, R2 had a magnitude of 18 kilonewtons times 3 meters. And we know that our resultant force is equal to 24 kilonewtons. Now, if we were to plug that into our calculator, we would end up getting that our location for our resultant force from point A is equal to 3.25 meters from point A. And just like that, we were able to finish problem 4.154. Once again, this problem was asking us to replace the loading by an equivalent resultant force and to specify that location from point A. So to determine our resultant force, what we did is we split this shape into two shapes that we could deal with, a rectangle and a right triangle. From there, we found that concentrated force of both of those shapes. Then from there, we also determined their locations. Our resultant force is equal to the sum of our two forces, giving us the magnitude of that equivalent resultant force. And then from there, to determine the location of our resultant force, we ended up using this equation. We simply plugged in all of the information that we knew into that equation, giving us that our location is 3.25 meters from point A. Thank you guys so much for watching this video. Please feel free to like this video, and also please feel free to subscribe to our channel if you guys would like to see more videos like this.